Hello everyone, welcome to my video. Today our lecture is the analysis of the parabolic cable used in suspension bridge, or you can call it cable stayed bridge. There are three spans of the bridge, one in the middle and there's other two on the sides. In the middle has a unique shape of the cable, and this is analyzed as to be in a parabolic shape, whereas the other two, the cable here is shaped in a catenary cable. These two cables here are totally different with each other. It has a different formula how to solve for the tension. The purpose of the video is to find the formula how to solve for the tension, the tensile stress sustained by the cable, all the cables, cable here and cable there and cable here as well. So, but we have to start the middle span, which has a parabolic shape type of cable. Alright, the cable here is analyzed to be in a parabolic shape, and here is the parabolic diagram, parabolic shape of the cable diagram. And here's the bridge itself, cable, and the load is W, and here are the necessary information you need to before we start our analysis. The L here is the horizontal span, the clear span between two towers, tower 2 and tower 3. The S is the length of this cable in a parabolic shape. The formula for S to solve for the length of the cable is right here in equation number 6. S is equal to L plus 8d squared divided by 3L minus 32 times d to the power of 4 divided by 5L cubed. That's equation 6. This is only applied to a parabolic shape type of cable. This cannot be applied to a catenary cable. Okay, they are totally different with each other. Okay, now in a parabolic cable at the distance L over 4, if this is your L, L over 4 distance, the shape of this segment of the cable, the shape of the cable is almost like still in a very straight line. You can see here I drew a parallel line to this segment of the cable, and they're almost like very close to the same straight line. So since this is a straight line, this is where our analysis will take place at distance L over 4. And here's the turning point at L over 4. This is where the cable start to shape like a parabola. So that's why this is a parabolic cable. Okay. And this is where our analysis will take place. All in this circle here, I isolated it in figure 1 right here. Figure 1 right here. And following the condition of equilibrium, the tension at A is also equal to the tension at B. This is point B and this is point A, simply because it is the same cable running and suspended from point B, tower 3 and tower A, the same cable. So therefore, following the condition of equilibrium, tension at A is also equal to tension at B. Remember that. Here we isolated this part of the cable, isolated in figure 1 to do our analysis. find the solution and tension at A. So this is the cable, the segment of the cable at L over 4. At this point here, the cable is still in straight line, therefore this is considered an inclined load. The tension here is a tensile stress. Stress is a load, so therefore this is an inclined load. So when you have an inclined load, you have to resolve it in two component of loads, one vertical and one horizontal, two components. The vertical load here is the load of the bridge, is WL over 2. The reason why this is WL over 2 is we are going to, here in our diagram, we are just going to analyze half of the bridge. Whatever we get this in the first half of the bridge is also applied to the remaining half of the bridge to complete the cable, and then it's because, reason for that is because of the condition of the equilibrium, that tension at A is equal to tension at B. So we analyze half, so that's why, figure 1, here we have the load. This is the known load, okay, WL over 2. This is the vertical component, and the horizontal component is the unknown. Okay, to solve the H in here is the unknown. So to solve for H, we have to equate the vertical component to the horizontal component of load. And so that we have this relation in equation 1. To form an equation 1, the H is the horizontal load, and the D is the distance from point A. This is point A according to our diagram, and H times D is equal to, we equate these two loads, alright? So HD is equal to WL over 2 times L over 4. L over 4, this is the like the lever arm of the load, and the lever arm for the H is the D in this direction. That's the lever arm with respect to point A. So we equate these two loads to get the HD. So HD is equal to WL over 2 multiplied by L over 4, and that's your equation 1. To solve this, P multiply L times L is equals to L squared. That's why we have WL squared divided by 2 times 4 equals 8 times D. D will go down by cross multiplying equation 1. We have the final simplification of the value of H, which is equal to WL squared divided by 8 times D, and this is your equation number 2. Now, if we examine equation 2, H is unknown, D is unknown. So in order for you to solve an equation, you only need to have one unknown. Here you have two unknowns, so therefore we have to solve the known value for D first, and then substitute it here to find the H. For now we have two unknowns, so we have to solve for D. This is in equation 2. To solve for D, this is right here in the diagram. To solve for D, D is the deflection of the parabolic cable when loaded. To solve for D is to draw a line from the top of these two towers, Tower A and Tower B, Tower 3 or Tower number 2, suspended cable right here, is to draw a line from the top of these two towers and then draw it to the midpoint of the parabolic cable. And from here, from the midpoint of the parabolic cable, draw the line, connect that line to point A right here to form a triangle so that we can solve for D. The angle of the parabolic cable is 20 degrees. So now I isolated this portion of the triangle from this analysis 2 in figure number 3 right here. So the L over 2 there is known, the D is the unknown, and the angle is known, 20 degrees. Therefore we can simply solve the value of D. And if this is your angle here in trigonometry, this is your opposite side. And if this is your angle here, this is your adjacent side. The opposite over adjacent is a function of a tangent in trigonometric function. There are 3 trigonometric functions: the sine, cosine, and tangent. The sine and cosine is not applicable here because there's no value for the hypotenuse. Sine and cosine contains a hypotenuse, so these sine and cosines are eliminated. So we're just going to use the trigonometric function of a tangent. So now, using trigonometric function of a tangent, solve for the tangent 20 degrees according to a diagram right here. Tangent 20 degrees is equal to D over L over 2. The L over 2 there is the clear span divided by 2 for the middle span of the bridge, for the mid span of the bridge. So tangent 20 degrees is D divided by L over 2. When you divide a number with a denominator in a fractional form, you have to, by rules, you have to multiply the numerator by the inverted denominator. This is the denominator. You have to multiply it to the denominator with an inverted. Multiply the numerator with an inverted. You have to invert this. Inverted denominator. That's why now it's equal to the 2 will go up there and then becomes the numerator, and L is the denominator. This is the final equation for the tangent 20 degrees. This is equation 3. Now from equation 3, from this equation now, equation number 3, we can solve for D. To solve for D is to cross multiply this equation. Cross multiplying equation number 3, 2 will go down and L will go up. So that's why the result is D. Simplification of the D now is equal to L times tangent 20 degrees divided by 2, and this is equation number 4. Alright, so now since we have D, we can substitute equation 4 to equation number 2 right here, the D. D is known now, so we can solve for H. Alright, so H is equal to WL squared over 8 times D. So we have the D now, which is the value, which has the value of L times tangent 20 degrees divided by 2. Substitute this equation 4 in equation 2 to solve for H, and once you get the H, now you can solve for tension at A using the figure in figure 2, using the analysis in figure 2. In figure 2 we have this vertical load WL over 2, and the horizontal load now is known. Since we solve for D, we can find the H. So we have the H now. This is known now, unknown, and this is the unknown. So you only need one unknown in one equation to solve for the unknown. Right? So TE now, using the Pythagorean theorem, the relation of the Pythagorean theorem, we can solve for the tension at A. So using Pythagorean theorem right here, I'm going to show you. We're going to go back to the arithmetic of the Pythagorean theorem in trigonometry. This is your triangle, this is your side A, this is your side B, and this is your side C. This is the hypotenuse. This is where the parabolic cable is analyzed to be an inclined load, right? So in Pythagorean theorem, the relation is equal to C squared. C squared is equal to A squared plus B squared. Okay, that's the relation using Pythagorean theorem. Now the solve for C To solve for c, we have to take the square root of c squared. Take square root of c squared, it will give you the value of c. And by rules we knew, take a square root from one side of this equation, the whole equation. To take a square root of one side of the equation, you also have to take the square root of the other side of the equation. So take the square root of c squared equals c, and therefore a squared plus b squared is also the square root of a squared plus b squared. This is the relation we're going to use to solve for the tension A in figure. This is the relation we're going to use to solve for tension A and relation in figure 2. Okay, now the H is known, WL/2 is known, the tension at A is unknown. Using that relation there, the c squared, the c is equal to the square root of a squared plus b squared, and this is your b and this is your a squared plus b squared. So G now is equal to the square root of, using this figure here in figure 2, WL/2 squared plus H squared. This is now the final equation to solve for tensile stress in a parabolic cable. This formula is only applied to a parabolic cable. This cannot be used in a catenary cable, the other two cable. So remember that this is a parabolic analysis for the cable in the midspan of the suspension bridge, and also the S. This is only applied to a parabolic cable, as we analyze this as the shape of a parabola. So this is the final equation now for the tension at A. It's equal to the square root of WL/2 squared plus H squared. Here we go. We have the solution of find the tension of the parabolic cable along this cable here from tension A to tension B. And don't forget the condition of equilibrium. Tension here is all the way the same up to the tension at B, but the distance d here is the deflection of the cable. This distance during construction has to be followed first, prior to the installation of this vertical cable that directly carry the slab of the bridge and transfer the load to the parabolic cable. And here we go, the tension there, tension at A, the tension of this cable here is formulated as we solved according to our analysis as a parabolic cable. T is equal to this now, WL/2 squared plus H squared, equation 5. So this is the solution now for the tension of the cable in a parabolic shape. We still have the catenary cable to be solved as well, right here. And these two here are catenary cable, and it has a different solution. The video here should be a little bit longer than the parabolic cable. This is much simpler than this one here. It's a little bit complicated to solve the tension for this cable. The reason that is the tower here is, tower number 3 is higher than tower number 4. This is the lower tower. I believe that the tension, maximum tension, it has two different tensions, tension here and tension here, has different tension, but the maximum tension, the largest tension will occur for sure by analysis right here. Alright, so you can wait, if you can wait for a little bit for the catenary cable. I will still gonna make that video and then upload it next to this one. Thanks for watching, and don't forget to subscribe. Your subscription is important. We're growing, and I know that the audience for this type of video is limited. if you're 9, 8, 10 years, 11 years old, you cannot watch this, you can't understand this. Only people that has a basic or complete understanding how this type of video is going to be understood. Alright, thanks for watching again, and bye for now.